All right, so on to a new type of reaction, alkene halogenation. So we are adding a halogen across a pi bond. So one halogen adds there, one halogen adds there. We see some potential products. The first step of this reaction is going to break this bond. And as we always think about organic reactions needing to go downhill for the most part, that occurs because it turns out that the halogen-halogen bond, so XX is what I'll write there. It could be Cl2, it could be Br2, it could be I2. It's a pretty weak bond, therefore it's pretty easily broken. So how does this reaction work out? I'm actually going to draw the first mechanistic step as two separate steps, but technically these first two arrows happen simultaneously, or these first three arrows happen simultaneously. So what I'm going to show is I'm going to show the pi bond adding to a bromine and the bromine-bromine bond breaking. And I'm going to call this step 0.5. So it's kind of half of what happens in this first step. But essentially we form a carbon-bromine bond, Br minus, and then the other thing that technically happens in the first step, but I'm kind of drawing it in two steps to show why this would happen, is that this bromine is actually going to add its electrons to that carbon as well to make a three-membered ring, which kind of seems weird, right? Because three-membered rings are unstable. But let's think about that for a second. So why would we form a three-membered ring to this bromine? So if we think back to like ranking resonance structures and all of those things, the most important thing about a resonance structure and the order of importance is everything having an octet. And while we might say this is going to be a strained ring, and it certainly is a really strained ring, what is the other option? The only other option would be to break one of those carbon-bromine bonds and have a carbon that doesn't have a full octet. So whereas this is step 0.5, this is step 1. So those two are both technically part of the same step. It would happen because we wouldn't want to have a carbon without an octet. How would we draw this if we wanted to draw it all at the same time? This is what it should be drawn as in a mechanism, where essentially the pi bond adds to a bromine. That bromine-bromine bond breaks and goes to the other bromine. So this Br minus has 4 lone pairs, as it would get 1 lone pair from that pi bond. And this bromine is going to use one of its other lone pairs to add to the other side of that pi bond. So essentially we make both this bond and this bond in the same step, but a way to rationalize why this three-membered ring is the better option is that if we don't have that three-membered ring, then we just have an open, empty carbon orbital and something that is lacking its octet. So this is the better option. What happens to get to our final product? Well, we have Br minus floating around in solution, and when it comes into contact with one of the two sides of that three-membered ring, which we call a halonium ring or a bromonium ring, in this case halonium for any of the halogens, that gets us to our final product. So this is step 2 of the mechanism. It's a two-step mechanism. So that being said, we showed both steps of that mechanism. What are the potential products, A, B, and C? Are all of them potential? Is one of them not a possibility based on the mechanism that we drew? So take a minute to think about that. You might want to look at some of these blanks, try and fill those in. Yeah. So you did that, and what we're looking for here is essentially this is really similar to an epoxide. And when an atom adds to one side of an epoxide, it adds to it in an SN2 type reaction. It has to add to the back face of the leaving group. So if both of these were wedges, it has to add to the back face, so the final, the carbon-bromine bond from that location, if this is what we're drawing here, this would actually lead to this product, because this is adding to the back face, it would have a wedge. So the halonium ion opens via an SN2 type mechanism. So the product, which product can't be a possibility? Well, this one's anti, right? This one, the bromine could have added to that side and made that. So the one that's not possible is, so we'll cross that one out. That one is not forming. So product B cannot form. What about the other two products? Products A and C form because that Br minus adds at either carbon. So it could add to that carbon there. It could also add to that carbon there. If it added to the one that we indicate, it would make C. If it added to the other one, it would make A. So both of those products are going to be possible. And this is an instance of exclusively anti-addition. The two atoms that were added to the opposite faces. So all of that in the books. Let's look at the next thing that is on the course packet. It says isomeric relationships. What is the isomeric relationship between the products? How are A and C related? Are they enantiomers, diastereomers, constitutional isomers, unrelated? What's the relationship there? And okay, you've answered. Good job. They have both stereocenters flipped. These two are enantiomers, so that is the relationship. All right, let's do another one of these. Okay, so now we're going to do another one of these halogenation reactions, and I want you to predict the product or products of this reaction here. So we have an alkene, we have I2. What is going to be formed as the product? So you pause the video. You are doing this right now. You've predicted your products. All right, I have 5 different things up here. At least one of them, maybe more, is not a product. So what I want you to now think about is which is not the product. So how do we do this? Well, let's think through this mechanism, right? So the I2 is going to add to one face, top or bottom of this molecule. We can draw part of that mechanism here. So the pi bond adds to the iodine. The iodine bond breaks, and it adds to the opposite face. It can either add to the top or the bottom. We'll just have it add to the top. So we'll do wedges to our I minus, or to our I plus. So we have our iodonium ion. And at this point, I minus, we have a secondary position and a secondary position. It's going to add to either of those positions, not preferentially. So if it adds to one side, it's going to make one thing. The other side, it's going to make the other thing. We'll just do that one. Okay. So hopefully if you pause it, I think this is a good time probably. We've talked through some stuff. Pause the video. Think about which products are possible. Okay, you did that. So these arrows that I'm drawing right here, which of these products would my arrows here go to? Well, this wedge, these double wedge to iodine, one of them's going away, right? This one's going away because that iodine is making a new bond there, which means that it's going to be a dashed bond to that. And this wedge remains, so these arrows would actually make that product. Okay, so those arrows that I have make this product directly. What other product is possible directly from here? Well, if we instead added those electrons to that position and opened up that way, these black arrows would make this product. So what is going on with the rest of the options? Are all of those not product, or are some of them product? Think about that for a minute. I'm going to make a model. You've taken another minute to think about that. Which of these is not product? So this, in any conformation, is product, right? So whether it's like that, and we have a bunch of single bonds, right? So I've actually taken the time to make that molecule as a model. And my red balls are the iodines. You can see that one of them's coming toward you, one of them's going away from you. So how does this molecule relate to this molecule? Well, here the carbons here, like 4 carbons in a row, kind of curve down, right? They go up, over, down. Here they go up, down, up. So we've taken the carbon skeleton and we've rotated around it when we're transitioning from this molecule to this molecule. So when we did that, what we're essentially doing is we are rotating around like this, getting all the carbons lined up in a zigzag, and now both of the iodines are wedges. They're both coming out at you just like this molecule right here. So what's the relationship between that molecule and that molecule? Those are the same thing. These are the same molecule. The same molecule. What else? This molecule is the same situation with that one. If we just rotate around that single bond, which again, single bonds rotate freely, all of them, all the time. Not all the time, but if there's enough temperature, if there's enough warmth in the room, which there is, then they're going to be rotating freely. So these are also actually the same molecule. So which one of these is the odd man out? Well, this looks like it's the anti-addition, but when we realize that we had to rotate around, so if we rotate 180 degrees around that bond, it looks like that. And we have a wedge to an I there and another wedge to an I here. So essentially that same starting conformation is how we have all the carbons, but now we've added those I's. So this is actually a syn addition product, which we know that in these halogenation reactions, they add anti. So both of these are not product. Neither of those are product because it technically wouldn't be addition here if it was product. There would have to be some difference of the starting material. So what would create that as a product? If we instead had this as a starting material. So what's the difference between that and that? This is a Z-alkene and this is an E-alkene. So the E-alkene would have made this, whereas the Z-alkane made that. So again, hopefully that all made sense. I think it was pretty clear. Yeah.